Okay, so here I'm recording another video for 113. So last time we finished lecture 17, slide 9. We practiced conservation of angular momentum, right? So there are again a lot of applications of angular momentum in real life. So a very common example is the ice skating and diving, okay? Because when look at the image on slide 10, right? So when the person is diving, the person always makes circles in the air, or when the ice skater is spinning, okay, the skater is also moving in a circle. So in this case, tell me that let's say the ice skating. I believe you have seen that, okay? Everyone should have that experience. When you see the ice skater pulls their arms in, do you see the ice skater spinning faster or slower? What's your answer? I hope everyone's answer is faster, okay? This is something you see in everyday life, right? And why does that happen? Have you ever seen that when the skater pull their arms in, they spin slower? You've never seen that, and because that cannot be done, okay? That's just not possible. Why isn't it possible? Why do they always spin faster when they pull their arms in? It's not they're trying to spin faster. They don't have to do anything. They just bring their arms in. They will spin faster. Why? Because of conservation of angular momentum. So take a look at this ice skater. So if you apply conservation of angular momentum, you would get this. And again, there's no force from the outside spinning the ice skater, right? The ice skater just spinning themselves. And then you will get IF omega F equals II omega I. Okay? Then let's use this equation to explain why they always spin faster when they bring their arms in. So let's say this is when they bring the arms in, final. This is when they extend their arms out. Let's compare these two I's, then we can see why they will spin faster. When they spin faster, their angular velocity just gets larger, right? Okay, so in this case, calculating the I of the ice skater is going to be very hard, but we can still just figure out if it's going to go up or go down when they bring their arms in, right? What is the definition of I? Well, you should do this. And so for ice skater, the ice skater is spinning about this axis, a vertical axis, right? So if you want to calculate this I, you would have to pick every little piece of this ice skater and then do m and then times r squared. When they have their arms out, think about if you want to calculate the I for these two arms, you're going to pick a little piece m here, m times r squared, m times r squared. You will get a larger number compared to when they bring their arms in. These two arms, they will be closer to the axis. So they will get a smaller I when they bring their arms in. So that means IF is going to be always smaller than II when they bring their arms in. Because every little piece on the arms is going to have a smaller radius with respect to this axis. Now, but the angular momentum must be conserved, so it's always going to be the same, okay? Because there's nothing from the outside spinning the ice skater. They're just spinning themselves. So that means omega final must be always greater than omega initial. You don't have to do anything, right? This is the law. Everything obeys the law. When they bring their arms in, they will always spin faster because angular momentum is conserved, okay? All right, so that's an application of angular momentum, okay? Now let's take a look at another example. Then we're going to move on to the next topic. Okay, and this is the good one. I really like this one. This is my favorite one this class. Let's take a look at this question. We all wish that time could go slower, especially when the exams are coming, right? Theoretically, there is a way to make one day longer. Why? Because what is the definition of a day? It's just a rotational period of the Earth about its own axis. So if you have some way to make the Earth spin a little slower, then you're making one day longer, right? How do we make the Earth spin a little bit slower? Theoretically, there is one way to do that, okay? So suppose all the people in the world line up at the equator and start driving a car right to the surface of the Earth. Because the total angular momentum of the people and the Earth is conserved, the Earth's rotation can be slowed down. Okay, so we're just going to decide to drive all the cars in one direction in order to slow down the Earth. Okay. So first of all, I want to ask you, in which direction should we drive the cars? This can be confusing to a lot of people, because we know that the Earth spins from the west to the east. And then if we have all the cars lined up at the equator, you want to make the Earth spin a little bit slower, everyone should drive the cars in which direction? You can use conservation of angular momentum. Think about it, because the total angular momentum of the system, including the Earth and everyone and the cars, it's going to be a constant. Or you can use forces to think about it. If you want to, the Earth is spinning this way. You wanted to slow down a little bit. You're going to apply force in which direction? And then in which direction you're going to drive the cars. Okay, this can be confusing. Think about it. What is the direction we should drive these cars? All right. So I'm going to tell you the answer. The right answer is A. We should drive to the east. Okay, this may be counterintuitive to people. Let's first think about force. Okay, we're more familiar with force. If this guy is spinning in that direction, right? This is Earth spinning from west to east. How do I slow it down? I would apply a force to the west, right? To slow it down. I'm not going to apply a force to the east. It's going to make it spin faster and faster. So I want to apply a force to the west. But when you drive the cars, the tires, you want the tires to apply a force on the Earth to the west. You should drive the cars actually to the east, right? If that's hard for you to think about running. If you're running, you want to apply a force to the west, to the ground. You're going to run this way or that way. You're going to run this way, right? Because when you run this way, your feet are pushing the ground in that direction, right? So you should run to the east if you want to apply a force on the ground to the west. So the cars are the same, right? The tires are rolling, okay? If you want the tires to apply a force to the west on the Earth, you should actually drive to the east, okay? So that's using force. And you can also think about this using the conservation of angular momentum, because the Earth and then the people, the total should be a constant, right? Should be a constant. They're all spinning to the east. In order to make this guy, in order to make this guy smaller, you're just going to increase this guy. So you're just going to make sure the cars are even moving to the east. So the cars are even moving faster than the Earth in that direction. Okay? So then this guy can slow down because the sum should be a constant. Either way, it should be consistent. Okay? Now let's do some math. We want to Okay, so that's the first thing we figured out. So you shouldn't drive to the west. If you drive to the west, you actually make the 1 day shorter. You're making Earth spinning faster, okay? Now, what if, okay, we decide that, okay, everyone in the world is going to line up at the equator and all start driving a car to the east. So that's going to make the Earth spin slower. Now I want you to estimate the required speed of the cars so that we can get 1 extra minute in 1 day. So this is going to be a long problem, but this is a very good exercise. And this also, I hope to use this problem to help you understand how to solve a real problem. You still have to make some simplifications, okay? And now we are just estimating, so it's fine that we make some simplifications. So we want to estimate the required speed of the car. So I'm going to still use conservation of angular momentum to solve this problem. So let's see how I can incorporate the speed in that law. So this is what I'm going to do. I'm going to call the Earth. I'm going to get a new marker. So I'm going to call the Earth I1. Okay? So that's one object. And then I2 is going to be the people plus the cars. Okay? And they are one system. Okay, so there's one system, including I1 and I2. It's like a system has M1 and M2, right? In rotations, I is equivalent to M. So I can just use I1 and I2 to represent different objects. Okay, and the people are sitting inside the cars, so I'm going to treat them as one object. Okay, so then what you should do is this, right? So all these, this I1 and I2, they're the system. So then the conservation of angular momentum, it's going to be this, right? And then again, there's nothing from the outside spinning the Earth, okay? So there's no torque from the outside. So the total angular momentum must be conserved, okay? So the total momentum of the system is going to be conserved. So that means what I can do is this. I have a system. The system has two objects, I1 and I2. Okay, this is really big, but it's an object. This has a lot of people, a lot of cars. Fine, that's another object to me. So set up, there are two objects rotating in this system. Set up conservation of angular momentum for the system. I1 omega 1f minus I1 omega 1i, right? And then plus I2 omega 2f minus I2 omega 2i equals 0. So it doesn't matter how weird it is, these two objects, I'm just going to always set it up the same way. Right? Now let's see. How do I calculate this i's? Okay, I is always easy, right? For example, the I of the Earth, you can again take a look at the list of the moments of inertia, so you can model it as a sphere. So I1, the equation I'm going to use is going to be 2/5 the mass, the Earth of the mass, the radius of the mass, the Earth squared. Okay. Now the I for the person, for the people in the cars, okay, that's a little bit hard to calculate. But so you can treat every car with the person inside it as a isolated point mass, right? How do you find the I for one car plus the person inside it? Okay, so if they are nice. If they are on the surface of the Earth, right? So they are rotating with the Earth. They're rotating with the Earth. So they are isolated point mass, how do I calculate the I for isolated point mass? You just do m times r squared, right? So you would just do m times r squared. And then, okay, the person and the car, they don't have the radius. The radius in this equation is going to be the radius of their circular motion. When they are spinning with the Earth, what is the radius of their circular motion? And that's just going to be the radius of the Earth, because everyone and the car are on the surface of the Earth, right? So they will move in a circle with the radius, just the radius of the Earth, okay? So that's just going to be m times big R squared. But that's just going to be the I for one car and a person inside, right? What about the mass? Well, okay, we want to do an estimate, right? So the mass of the car, let's just use a typical number, 1,500 kilograms, okay, including the person, okay? So that's a typical number. The R is still going to be the radius of the Earth. But what about, because if there's only one person driving a car, that's not going to help, right? So that's why we're going to assume everyone, all the people in the world, will decide to line up or drive a car at the equator. So that means you will have a lot of these I's together, right? So what is the total I for the people and the cars? You're going to do this I, you're going to add all these I's together, right? So basically, you're just going to use the number of population, the world population, times this I, okay? And what is the population? Last time I checked, so this is going to be number of person times m r squared. Okay, and then the last time I checked, well, the number can be a little bit different now. 7.6 billion. Okay. So this is a big I, but I1 is also a big, right? I2 is also big. If I2 is too small, it's not going to make any change here. Okay. We want to make I2 very big so that we can change the the angular speed of the Earth. Okay? So now, okay, I'm going to leave them here because I can calculate these numbers, right? This is going to be a huge number, the I for the Earth. This is also going to be a huge number. The mass, I'm going to use 15 kilograms. The world population, 7.6 billion. That's the number I checked. Well, this is not like a valid assumption because not everyone can drive a car, right? If you're too old, you're not allowed to drive. And then if you're a kid, you're not allowed to drive. But we're just making an estimate. That's fine, okay? So these two I's I can calculate. So I don't need to worry about these I's, right? So I1, I2, don't need to worry about it. Now, omega 19, so this guy, I know how to calculate that. I'm just going to do the math at the end. Now, omega 19 and omega 2I is when no one is driving a car. Everyone is just standing on the Earth, ready. Okay, we're just getting ready. So that means initially, everyone and the car are spinning with the Earth together. So they will have the same initial angular velocity, right? So, okay, so that helps. So that means omega 1I and omega 2I, they're going to be the same. I'm just going to call it omega I. Okay, then how do I find omega I? So that's just going to be the angular velocity of the Earth right now. How do I find the angular velocity of the Earth right now? Remember, what is the definition of angular velocity? That's going to be changing angle divided by changing time. And when something is rotating, we usually just use the period as the time, and then if you use the period of the time, what do you put at the top? The angle for one period, it rotates. That's just going to be 2 pi radians or 360 degrees. Now I'm using SI units. I should use radians. Okay, so that means the omega I is going to just be 2 pi divided by Ti right? And what is the TI? TI is the current period of the Earth. What is the current period of the Earth? That's just 1 day, right? And that's just 24 hours, okay? So I already know TI. TI is just going to be 1 day. So let's write 24 hours. Okay, I already know how to calculate this and this. Okay, so I still have two variables here, omega 1f and omega 2f. First of all, omega 1f and omega 2f, they're not going to be the same. Because when we are driving the car, right, we are not moving at all right now. We already have some angular velocity, which is the same as the Earth. But if I say I'm running, then that means I'm moving actually faster than the Earth if I'm running to the east, right? Because I will already have the velocity of the Earth, and then I'm also running on the Earth, so I will get actual. Think about if you're running on a train, and to an observer, stationary observer, your speed is going to be, the train already has a speed, and then you add that to your speed relative to the train. Right, so you will get a larger speed. So omega 2f, if everyone drives to the east, the Earth is already spinning to the east. So omega 2f is going to definitely be greater than omega 1f. Remember, omega 1f is for the Earth. But we can first calculate omega 1f, right? What is omega 1f? Omega 1f is going to be this. Well, that's still 2 pi over TF. Okay? Then what is TF? That's going to be the final period of I1. What is I1? Oh, Earth. So that means I want the final period of the Earth. What is the final period of the Earth? What's our goal? Our goal is this. I want to get 1 actual minute in a day. So I want the period of the Earth to become 1 day plus 1 minute. That's the final period I want. Okay? That's going to be the number I plug in. Of course, you're going to convert everything to seconds. Okay? So the final period is going to be 24 hours plus 1 minute. Okay? Now you see that this guy, no question. Well, I will do all the algebra to find these numbers, right, at the end, but that's fine. I'm going to do that at the end. First, I want to just figure out the math, how I'm going to get the V involved. So you see, this is good, this is good, this is good. The only thing I don't have is going to be this. And this guy will include the V, okay, why? So what is the relation between the omega 2f and omega 1f? First of all, we just figured omega 2f is going to be omega 1f greater than that. Because if you don't move, you already have the angular velocity of the Earth. You're moving with the Earth. It's like you're standing on a train. What's your speed? You already have the speed of the train, right, to a stationary observer, right? If the train is moving with 5 meters per second, you already have 5 meters per second. And then if you're running on the train, so your total speed is going to be sum, so you're going to be greater. So that's what you do when you're on a train, right? So if you're running on a train, the train's moving, you're also running, okay? So the train is moving at like 10 meters per second. You are running at 2 meters per second. What is your speed? Your speed is going to be 10 meters per second plus 2 meters per second. No question, right? Now I'm going to apply this to this. If these cars are not moving, they already have the angular velocity of the Earth, which is omega 1. Yeah. But then when these cars, they're also moving to the east, they will get this, right? Plus their speed, right? So it's pretty much the Earth already has 10 meters per second. I'm standing here, I already have 10 meters per second to any alien from the space, right? But then if I'm running at 2 meters per second to the alien my speed is going to be 10 plus 2. Now we're just doing angular speed, but they're going to be the same, right? The Earth is already rotating. Everyone already has the angular speed, but if you decide to drive a car in the same direction, you get some extra. You get some extra. How do I find that extra? You're going to add angular speed, actual angular speed to this. That's going to have the speed involved, right? If you are driving with the speed of v relative to the Earth in that direction, how do you find the actual angular speed, the relative angular speed you get relative to the Earth? You just do v divided by r, right? You already have the speed of the Earth. Now you're driving to the in the east direction with an actual speed v. Okay? So if you want to find your speed, you would do the speed of the Earth plus this v. But now we're doing angular speed. So I'm just going to do the angular speed of the v of the Earth plus this actual angular speed. How do I find the actual angular speed? I'm just going to do speed divided by radius, because they're always connected by radius. Okay? So now you see I already have everything, because omega 1f, I can find it. The only one I know in this problem is going to be this v. Then you can put everything together, rearrange this equation, and find this v. Okay? Okay? The algebra is going to definitely be lengthy, because there are a lot of numbers. You're going to find every number. Okay? Because the problem never didn't give you I1, I2, omega 1f, omega 1. No. You're going to find every number, as I just said. But once you have all these numbers ready, plug them in, rearrange this equation carefully, you will find this v. Okay? So let's do that. I want you to also pause the video and do this for me. Okay? So I'm also going to do it here. But remember, what I always do is this. I plug numbers in at the end. I will first do the algebra with the symbols, and then see if I can simplify this equation, and then get rid of a lot of things. Okay? So that's what I'm going to do here. So I'm going to list this there. Okay? So these are all the numbers I'm going to calculate. And the omega 1f is here, and the omega 2f, it's going to be omega 1f plus this required speed over the radius of the Earth. Now I'm going to rearrange this equation a little bit and see if I can simplify it so that at the end I don't need to do a lot of algebra. So I'm going to rewrite it. Okay? So I'm going to do that here. I1 omega 1f minus I1 by 1i. Okay? I hope you have done the math yourself already. Okay? The first thing I would do is that, because I know that omega 1i and omega 2i, they are the same, right? So I can put them together. Okay, I'm putting these two guys together, and then I'm gonna put this I1 omega 1 I plus I1 omega 2i. All right. This is what I want to do. No, I don't want to remove that. Okay. I'm just going to put these two guys together, and then minus, okay, minus I1 plus I2 times omega I. Okay, that's what I want to do. Okay? I put these two terms together. But these two initials, they have the same omega I, so I can factor out omega I. Now this guy, let's see, because omega 2f equals this, so I'm going to rewrite omega 2f as omega 1f plus v over the radius of the Earth. Right, I'm just using this big R. Now I'm going to distribute this, and then you will see why I want to do this. All right, now you see that now these two terms both have omega 1f, so I can combine them. I would get I1 plus I2 omega 1f, right, plus I2 V R over R minus I1 plus I2 omega I. I still haven't plugged any numbers in because I want to see if I can simplify the algebra, okay? Then you see that I can combine this term with this term, because this is I1 plus I2 times something. I1 plus I2 times something. So you put them together, you can factor out I1 plus I2. So you will get I1 plus I2. You put these two terms together, you will get omega 1f minus plus I2 V over R equals 0. Now don't forget what we're doing. I'm trying to find the V. So move this whole thing to the right, and we'll get I2 V times R equals I1 plus I2. Then it's going to pick a negative sign on the right. So basically, just switch these two terms. You will get omega I minus omega 1f. Now find expression for V. So V is going to be equal to multiply both sides by R. Divide both sides by I2. Okay, and that's pretty, well, there's one more thing I can do. I'm going to divide this whole sum by I2, okay? So I can separate them. I put these guys on the side. So V is going to be this guy divided by that. This owning this. Divide this by I2. What do you get? You will get I1 over I2. But if you want to plug numbers in, I think this is already very simple. Plus 1, right? If you divide I1 by I2, that's what you get. And this is still there. I think this is the simplest you can get. Now you plug numbers in. It's going to be easier than you plug numbers in at the end. Okay? So now let's see. I'm going to erase this. Okay? So as I said, I1 you can calculate using that number, right? So let's see. No, I can plug numbers in now. Okay, I'm going to plug numbers in now. I1 is going to be 2/5 mR squared divided by I2. How do I find I2? It's going to be the number of people times the mass. We assume is 1,500 times this R squared. So 7.6 times 10 to the 9th. That's the world population. 1,500 kilograms, and then R squared. So you see R squared are even going to cancel. So this is the first thing. Now this thing times omega I minus omega 1f. Omega I 2 pi over the initial period. That's going to be converted to seconds, 24 times 60 seconds. Okay, minus omega 1f Omega 1f is still the angular speed of the Earth, 24, 60 seconds, plus 1 minute, plus 60 seconds. This is the denominator for the second term. Then this thing, okay? And then multiplied by the radius. Now the radius is not going to be canceled. You're going to plug it in. But these two are going to cancel. Okay? This is the simplest that we can get. Now you put numbers in carefully. You will find the required speed. It's going to be okay. So we spend a lot of time figuring this out, and this is a very good problem. This is, you see, solving a problem in real life, it's actually really hard. This is still a simplified problem for this class, but still you see that you have to calculate all, you have to consider all the factors, you have to pick a right law, you have to build a very good model, okay? Sometimes you still need to simplify things a little bit, okay, if you're just making an estimate. But anyway, make sure you understand everything. You can do this, all the algebra, okay? At the end, you will find that even if we want to get 1 extra minute in a day, we're going to drive these cars. Everyone is going to drive these cars at this speed. And this is definitely ridiculous speed. Why? What is the speed of light? 3 times 10 to the 8th meters per second. First of all, we can't achieve this speed right now. But if you would say, what about like in 1,000 years? We still cannot, because this is faster than the speed of light. Okay? So this is not going to work. At least this method is not going to work. Okay? Because you can never make a car or anything faster than this. So I'm sorry, we can't get the 1 extra minute. Even for getting 1 extra minute in a day is impossible. So, you know, just deal with it. It's always 24 hours, okay? So don't waste your time, especially before the test. Study hard before the test. Start early, okay? All right, so that's that. So we did spend a lot of time solving that problem. Now let's come. Now it's just the summary. Slide 13, okay? So again, we have learned several laws here, but we just learned different versions of the laws we already learned in linear motion, right? So Newton's second law is the first law we learned, right? And then kinematic equations. When do I use Newton's law and kinematic equations? Constant torques and constant angular acceleration, right? When do we use Newton's second law in linear motion? That's when everything is a constant, right? Because when everything is constant, you can use Newton's second law to find the acceleration, plug the acceleration into the kinematic equations, and do kinematics. It's the same idea here. When you see constant torques, constant acceleration, constant angular acceleration, you can try Newton's second law. The new version of Newton's second law, right? Net torque equals I times F, and kinematic equations. When you see different heights and rolling objects in a problem, okay, most likely I'm going to use working energy. But again, because different heights can get mgh involved, right? Rolling object always have 2 different versions of kinetic energy. So that's probably what I'm gonna do when I see rolling objects and also different heights. When do I use conservation of, that's when I use working energy, right? When do I use angular momentum? The last thing we just learned. When there are different forms of energy involved, like the sun problem, okay? The sun becomes a red giant. It's a nuclear reaction. There's a nuclear energy involved in that process. So we can use that conservation. Well, you can still use conservation energy, but it's going to be hard in this class. So we use the conservation of angular momentum, okay? And then if there are humans involved in the problem, always use conservation of angular momentum, because the problem we saw, we can do work to the outside, right? Because human, it's really complicated, okay? So we can convert energy to different forms. So in that case, it's a little bit tricky if you want to use conservation of energy, because you need to keep track of different forms of energy from the human. So in that case, we always use conservation of angular momentum when you see humans involved, right? Like the student and the platform problem, you use the conservation of angular momentum, and we also checked that the kinetic energy is not going to be the same. Some of the energy from the student has been converted to the kinetic energy. So if you consider energy is actually a rather complicated process. But if you just set up conservation of angular momentum, still easy, right? Because angular momentum is always I times omega. All right? So that's this. Now, let's see. So we have already finished this. So the next part, we're going to move on to the next lecture. The lecture 18, okay? So lecture 18, so there's a very special topic in this part, which is called rigid object in equilibrium. But we're not going to learn any new laws in this part, okay? We're just going to apply Newton's second law in a rigid object in equilibrium to solve Newton's second law. But we do have two different versions of Newton's second law, right? The first one is the real one we learned in linear motion. Net force equals mass times acceleration. When something is in equilibrium, that means it's not moving. When it's not moving, easy, no velocity, no acceleration, right? So the net force on this object must be always zero. So that's the first law we're going to set up when we solve a problem, with objects in equilibrium in this part. But remember, when you use this condition, the force, you're going to break it into x and y components, right? Because x and the force can be in different directions. You don't just add them directly. Okay? So the net force on the object is going to be zero. But we also learn another Newton's second law in this part. So for a rigid object where the size of the object, the shape of the object cannot be ignored, if this guy is not moving, it's not rotating, it should also satisfy the second, the other version of Newton's second law, which is the torque. And that torque must be I times alpha. But if this object is in equilibrium, that means this object is not rotating at all. That means it doesn't have any angular acceleration, okay? So that's going to be also zero. So looks like you have two equations, but you don't only have two equations. This equation is always going to give you two equations, right? Because when you apply this equation, you will do that in x direction and y direction. So you will have two equations from the force equation, the force condition, right? And we have done that before. We have done that many times in Newton's law. This guy can give you multiple equations. Why? Because when you calculate torque, you need to pick a pivot, right? You need to pick a pivot. Sometimes there is a real pivot in the problem, okay? Then you can go ahead and pick that pivot. Sometimes there's no real pivot in the problem, but that gives you actually more freedom. You can pick any point as your pivot and set up this torque equation. So this equation can actually give you multiple equations if you pick different points as the pivot. Okay? So actually these two equations, they can give you many equations. At least this is already at least two. And this guy can give you another few equations. But usually depending on how many unknowns the problem has, we just need as many equations as the number of unknowns, right? If there are three, we just need three equations from the problem. Okay? So we're not dealing with new laws. We're just dealing with the Newton's second law, the two different versions of Newton's second law, and in a very special case, when the objects are in equilibrium. Okay? And then we're going to see some examples next time.